All right. Hey everyone. Hope you're having an okay day. Uh, I know it's still early, some comparatively. Uh, yeah, just a few weeks left in the course. We're heading towards the end. Switching over, as far as this course is concerned, we're switching over from electricity and magnetism. We're transitioning to optics. So we'll take a look at that. I know it's a busy time for everyone. There are projects and final papers and theses, and if not that, there's also pre-registration and so on. So good luck with all that. Let me know if you have questions, or if there's anything I can do to help. And yeah, you can always, besides my regular office hours, you can also just email me and ask to Zoom at a different time, and we can set something up. Okay, so last time we were talking about the Poynting vector, which we denote as S, and it comes from the cross product of E and B, and we have a factor of 1 over mu naught. And we said, okay, it points in the direction of the flow of electromagnetic energy. And today we're going to talk about electromagnetic waves. So before I start on that, any questions first? Okay. So let me share my screen. And all right. So an electromagnetic wave, if we just look at um, one series of points, and use the pointer here. Right. If we just look at one series of points, we'll see that we get a series of electric and magnetic fields, which for the simple case, we can look at they are varying sinusoidally. And so let's notice a couple of things. So here the gold vectors represent the electric field, and the blue vectors represent the magnetic field. So we see that they are perpendicular to each other. We see that they increase and decrease in sync. So for electromagnetic waves in vacuum, these are two consistent properties. Now, if you have them traveling in a waveguide, or which is a sort of kind of conducting channel, sort of like a chimney for electromagnetic waves, you could say. So if you have in such a case, then they don't have to obey all those properties. You can have them be not perpendicular to each other, and so on. But if they're just traveling in empty space, or if they're just traveling through glass or air or something like that, the electric and magnetic fields in an electromagnetic wave will be perpendicular to each other, and they will increase and decrease in sync. So I've actually, this is a still from an animation. I'll try playing it here, but because of frame rates and such, it might not appear all that properly to you. If it doesn't, don't worry. I have put the file on Moodle, so you can play it yourself. Hold on, I have to share that for you as well, otherwise you won't see what's going on. Share screen. There we go. So it might appear a little jerky to you, but like I said, I've put this file on Moodle so you can download and play it yourself. And I've put links to a few other simulations and visualizations on Moodle. All right, so it is quite hypnotic and nice to watch, but we will go on. Oh, Sally, question, yes.
Okay, so these are, I'm confused, like what is, so this is a point, these are points? What, like, what are we talking, what does this wave represent?
Okay, what we are doing is we are looking at
You said
Uh,
it was a point or a series of points or
a
something?
series of points. So basically, we're looking at what is happening along the x-axis.
For what?
For the electric and magnetic field. So we're looking at the electric and magnetic fields along the x-axis, and what we see is that they vary with time, and also like different points will have different field strengths.
Okay. So like a point in space?
Yeah, different points in space. So if I pause this video, we can see that even at the at the same moment in time, like different points are seeing different electric field strengths, right? Like this point here is seeing no electric field. Sorry, I forgot. The gold ones are the electric field. So this one, anyhow, we see there's no electric field here. But here at this point, we see that, oh, it's actually seeing a very strong electric field at this point.
So is the x-axis time or space?
Uh, so we haven't shown any time axis here. The time is shown by the animation.
Oh, okay. So this is all just okay.
This is all space. Yeah, this is all X, Y, Z. Yeah.
Okay, and the x-axis, so it's traveling through space on the x-axis.
Yeah, the wave is traveling in the X direction. That's right. So if we look at points along the x-axis, what we see is that at each point, if you just focus on a single fixed point, so I'll start the animation and leave the pointer at one spot. So if I just look at one fixed point, we see that at a fixed point, it like goes from zero field to a large field to zero field to large field in the opposite direction, and so on.
The flux is changing.
Say again?
Does that mean the flux is changing?
Well, remember, to define flux, you need an area. So, but even without talking about an area here, if I just look at the field strength at that point, I can see the field strength is changing.
Okay. And what changes the field strength?
So this is, remember, it's a self-propagating wave. So what's happening here is that like the changing electric field makes the magnetic field change, which makes the electric field change. And so they end up changing in sync. If we solve the equations, what we see is that they increase and decrease together, but they're basically reinforcing each other.
Oh, so like the B field makes the E field change and vice versa?
Exactly, yeah.
Okay.
Other questions?
So once it starts, it just goes forever?
Pretty much, yeah. I mean, like once you shine a light, the light beam just keeps going until it's absorbed. Yeah, until it's absorbed.
Is that kind of like infinite energy?
I think there were two questions. So was that Harrison and Katie, I think? Or,
yeah.
Isn't that kind of like infinite energy?
okay, so first Harrison's question, then Katie's. It is, no, it's not infinite energy. I mean, it's energy that will just continue propagating. So here I'm showing it as a steady beam of light. And so this will just keep on propagating out. But you could imagine that I just flicked a torch on and off, in which case you'd get a pulse of these electric and magnetic fields, and that pulse would travel through space. So, you know, where the pulse is, you have energy. Where it is not, you don't have energy. Does that answer your question, sort of?
Yeah.
Okay. Katie.
I'm just wondering, is it how the electric field generated by a current carrying a wire looks like?
No. Well, at least depends on what's happening with the current. If it's a steady current, it would not look like this. It would be steady. It wouldn't be changing with time. So here, the crucial thing is you need, to start this off, you need a field that is changing in time. So you can create that by accelerating a charge. You can create that by running an alternating current through a specially designed antenna. And there, because the current is running back and forth and the fields will change periodically, and that will give rise to an electromagnetic wave.
Okay. Thank
And
you.
then Sally, I think you had a question too?
Yeah. So are all electromagnetic waves light waves? Like light?
Basically, yeah, there is no essential difference between any electromagnetic wave. The difference purely lies in their frequency and wavelength.
Okay. So how do you know this was a light wave?
Oh, when I say, okay, that's a fair point. When I say light wave, I'm talking generically. So I mean an electromagnetic wave.
Okay, so you use them interchangeably. Okay.
Yeah, I will use them fairly interchangeably, yeah.
Okay.
If I want to be specific, I might say like visible light to refer to the optical frequencies that we usually see.
Why doesn't one field trail another?
Yeah, that used to trip me up too. Basically, that comes from the maths. If you solve the equations, you see that the solution shows that they actually vary in sync.
And then like what makes, when it gets really, really small, what makes it get large again?
Oh, because even though it might be zero at that point, at the neighboring points, it's not zero, right? And so it continues getting energy from the neighboring points. And so it keeps moving.
So we're thinking of this as more than one particle.
We're thinking of this as looking at all the points along the x-axis. So there aren't really particles here. There are points at which you are examining the electric and magnetic field. But yeah, you're looking at all these points along the x-axis and seeing how the electric field and magnetic field change.
Okay, thank you.
Mm-hmm. All right, okay, so we know that the E and B fields are perpendicular. And in this case, we can see that, yes, it's clearly moving in the X direction. Is there something we can do to tie this together? Yes, so the pointing vector. So if remember, the pointing vector is given by E cross B. So if you try that over here, let me just pause this for a moment. So just try, the gold one is at the E field. So curl from the gold to the blue, and you see that, yeah, your thumb points in the positive X direction. It is pointing in the direction that the wave is moving. That is the direction in which the field, in which the electromagnetic wave is transferring energy. And you can see that no matter whether you look at it over here or over here, you get the same direction for the pointing vector. Because even when the E field reverses, so does the B field. And so that keeps the direction of the pointing vector the same. Right, so remember, gold to blue, in this case, so E to B, curl it that way, and you'll see your thumb points in the positive X direction. Okay, so I'm going to close this and go back to the slides. Stop share. Okay, so let's remind ourselves or learn or see for the first time a little bit about waves in general. So if we consider some function of x, and it's a pulse function, so it's mostly zero, except in a small region where we can see that, oh, okay, it's got a pulse there. And I'm going to set my origin actually at this point, at the peak of the pulse is going to be at x equals 0. So this is just f of x. This is just a function of x. But now what if I create a time-dependent function, g, which is going to be a function of x and t, and what I do is I write it as f of x minus vt. So what is going to happen? Obviously, the graph that we see is going to change as time changes. How is it going to change? So okay, no, I'm not going to go through the question. I'm just going to kind of take you through it. So the question is asking, at what value of x is the peak of g? Remember, g is f of x minus vt. if I can write that down. But yeah, where is that peak at t equals 2 seconds if v is 2 meters per second? So let me sort of explain what's going on here. Use draw. Okay, so we're saying g of x and t is equal to f of x minus vt. So we know that the f graph will peak when its argument, right, when this is the argument of the function, right? So whenever this argument is 0, that is where the peak will be, right? So what we see now is that as time progresses, as time progresses, we see that where x, the value that x should have in order to make this whole thing 0 will change, right? So what that means is that the pulse is traveling, right? The peak of that pulse is traveling. So when t is equal to 2 seconds, right? And we're told that the speed of the wave is 2 meters per second. So then we do vt gives us 4 meters. So it tells us that, oh, okay, we'll need x equals 4 to find the peak. All right, because then we'll have 4 minus 4, and we'll get f of 0, which is where we know the peak is. And we can see that as time increases, because v is a constant, as time increases, x also has to increase. So we see that this describes a wave that is traveling in the direction of increasing x. Question, yes, Sally.
So we know that it peaks at 0 because the original function peaks at 0?
Yes, that's right.
Okay.
So, so this is the great thing. This now, f of x minus vt, it doesn't even have to be this particular graph. Any function, right? If you take any function of x and you replace everywhere, you replace x with x minus vt, that now becomes that same graph, but now just constantly traveling to the direction of increasing x. Right. So this is the solution to the wave equation. And to sort of illustrate that, just stop the share for a moment and focus here. So if we have f of x minus vt, so remember that I can do a partial derivative with respect to x of f. And what does that do? That treats everything except x as a constant, right? X is the only variable then. So if I do this, I'll just get, okay, let me clarify this. So let me say that, yeah, let me define this variable u is x minus vt, okay? So then if I do partial f partial x, that will be the same as partial f partial u times partial u partial x, just by the chain rule, okay? And we can see that partial u partial x is just 1. So this just becomes partial f partial u. All right, I can do a second derivative. So I take one more derivative with respect to x, and what I end up with is the second derivative with respect to u. All right, but now what if I take a derivative of f with respect to time? Okay, so I can write that as partial f partial u partial t, where remember u is x minus vt. So when I do partial u partial t, what do I get? I get minus v. So I get minus v partial f partial u. And v is a constant, so I can take one more derivative And what I end up with is another factor of minus v. So I get v squared times the second derivative of f with respect to u. So
How do you get v again?
that comes from the partial u partial t, because x
Oh,
dt, yeah.
right. Okay.
Right, so if I put this together, what do I end up with? I end up with second derivative of f with respect to x is, let me make sure I got it. Yes, is 1 over v squared times second derivative of f with respect to time. Okay, because if I look at this side, I have just second derivative of f with respect to u, and if I look at this side, I have 1 over v squared times second derivative of f with respect to u. Right, but this is the wave equation in 1D. And so what we have shown is I've said nothing about f. All I've said is that you should be able to take derivatives. You should be able to take two derivatives of f. That's it. So any function of f, any function f, if you make it of f of x minus vt, that becomes a solution for the wave equation, and that describes a graph or whatever, a function moving in the direction of increasing x. Okay, so if that is a wave traveling in the positive x direction, then so x minus vt wave traveling in positive x direction, then you can guess, and you would guess rightly, x plus vt will be a wave traveling in the negative x direction. And the way to keep it straight is simply to remember, as time increases, how does x need to change in order to keep x minus vt the same? So here, as t increases, x also has to increase to keep x minus vt the same. And here, if t increases, x has to decrease in order to keep x plus vt the same.
So for the wave equation, the f, we got like partial derivative of f, like 1 over v squared partial derivative of f over partial derivative of t squared. And then the f is, and if it's moving in the positive direction, that f is x minus vt.
That f is some function of x minus vt. So it could be sine of x minus vt, it could be cosine, it could be like pretty much any function that you can take two derivatives of.
Okay.
So yeah, I could have sine of x minus vt, I could have e to the minus x minus vt squared. So it would be like a Gaussian graph, just constantly moving to the right.
Okay.
Yep. So f can be anything. All right. So what terminology do we use to describe waves in general? So let me skip over this. And we said, okay, x plus vt, pulse traveling to the left. All right, so in general, we're going to look at sinusoidal waves simply because they have certain nice properties. And so we will often write them in this form. well, we said it could be any function of x minus vt. So we'll put this constant factor k out there, and then we can distribute that. So it becomes kx minus kvt. And then we rewrite that as kx minus omega t. And so the terminology here is, in this case, I'm writing y as a function of x and t. We're going to be writing stuff like electric field as a function of x and t. So this would be, the factor out here is the amplitude. V is the speed of the wave. K is the wave number, which we'll show is related to the wavelength. And omega is the angular frequency. So, okay, skip. All right, so yeah, so just some illustrations. So for plotting this function, so I'm freezing it at t equals 0. So I look at only the x dependence. Then the amplitude is well, half of, when you go from the peak to the trough, half of that is the amplitude. Or you can say the full thing is 2 times the amplitude. And the wavelength is, if you freeze it at a given moment, then how far do you need to move in the x direction to go from either from one peak to the next peak, or one trough to the next trough, or you're going from this 0 point to this 0 point. We can't stop here, because here you can see that the shape of the wave here, it's increasing, but here it's decreasing. So to get a full repetition, you need to go all the way till here. All right, so if instead I stay at one point, so I'm supposing I'm staying at x equals 0 and letting time vary, then even if I'm staying at one point, I see the wave passing by me, and so I see this variation. And so then now the time period is the time I need to wait from one peak to the next peak, or one trough to the next trough, and so on. All right. So to summarize stuff so far, so the time period is related to omega. Time period is 2 pi over omega. And you can also write it as 1 over f, where f is just called frequency, omega is the angular frequency. And the wavelength, lambda, is related to k, the wave number, in a very similar way. It's lambda is equal to 2 pi over k. So if you measure lambda in meters, then k would be measured in radians per meter. All right. Similarly, f is measured in per second, seconds inverse, and omega is in radians per second. We sometimes use hertz to refer to frequency, and 1 hertz is just 1 second inverse. All right, so, and then the speed is actually related to omega and k. So if you do omega over k, that will give you the speed v. Or you could also do lambda times f. So wavelength times the frequency. And you can see that that will give you like meters times per second will give you, yes, meters per second. Sally, yes.
Okay, so wavelength, I'm still a little confused about what wavelength is. So it's like the number of like the number of
it's wavelength or wave number?
a wave number.
You can just think of it in terms of like, so k would be 2 pi over lambda.
Oh, that makes more sense. Okay.
Yeah. Yeah. We'll talk later about other ways you can interpret it, but it's often easiest just to go back to 2 pi over lambda. All right, so let's skip over this one. Okay, so as I was mentioning earlier, all electromagnetic waves, they're just, the only thing that differs is what their frequency is or what their wavelength is. And because the speed of light in vacuum is constant, as the frequency increases, the wavelength decreases, right? Because remember, lambda f is equal to v. So if v is constant, then as one goes up, the other goes down. And what we think of as light, to be more specific, visible light, is just really a very narrow band in the electromagnetic spectrum. So violet light is on the order of 400 nanometers in wavelength. Red light is on the order of like 600. You can go up to maybe like 630, 660 nanometers in wavelength. So in other words, even if I'm being very generous with the bounds, in less than the wavelength variation is like 300 nanometers at most, going from like 400 to 700, rounding. And that leaves so much more space, right? You can go to much shorter wavelengths. And so you go to shorter wavelengths than visible, you get to ultraviolet, then to X-rays, and then to gamma rays. If you go to longer wavelengths, you get infrared, you get microwaves, you get radio waves. But this is all electromagnetic radiation. And there's no real hard boundary. So like what you call an X-ray and what you call a gamma ray, there's a lot of overlapping territory. So some people will talk about hard X-rays, but then other people will call the same thing a soft gamma ray, and so on. So it's really just a matter of perspective there. And it turns out that the energy of this radiation, if you just look at a single pulse, it's tied in with the frequency. So the higher frequencies usually have higher amounts of energy. So that's why gamma rays are more penetrative than X-rays, which are more than ultraviolet rays, and so on. Which is why ultraviolet rays can, if you're overexposed, can cause cancer, because the energy there is causing mutations in your DNA. And obviously there's a limit to how much X-rays you should be exposed to. Yeah. All right. Any questions? Okay. All right. So we've already noted some of these points. E and B are in phase. They're perpendicular to each other. And you do the cross product of E and B, and you can get the direction of propagation. It turns out their magnitudes are also related. The speed of the wave, of an electromagnetic wave, is given by the amplitude of E over the amplitude of B. And surprisingly, the units work out. So we know that electric field is measured in either newtons per coulomb or volts per meter. So you take that and divide it by Teslas, and surprise, you actually can show that it works out as meters per second.
How did they figure, how do you know that's true?
Well, okay, let's see. So to do that, we'll need to relate the Teslas. What would be the easiest way?
I didn't mean the units, I meant the velocity, like just.
Oh, I see. The relation between V and E naught and B naught. That comes from when you apply the, when you look at the wave equation solution, you can find it from there.
Oh, okay.
Yeah. All right. So let's see. Let's skip this one. All right. So we now, to get more detail in terms of how we describe the waves, what we do is we introduce this idea of polarization. And polarization simply is focusing just on the behavior of the electric field. So here, remember the gold ones are the electric field. So the question is, which plane is the plane of polarization of the wave? So we see that if we're just looking at a snapshot, we see that, oh, okay, the electric field all these vectors lie in a certain plane. right? And that's the plane composed from the direction of the E field, which is in the plus Z direction, and the direction of propagation, which in this case is in the Y direction. It doesn't have to be plus Z, actually, you can do minus Z as well. But basically, all the electric field vectors lie in the YZ plane. So we say that that is the plane of polarization of the wave. So, all right, so we'll come back to polarization in a little bit. All right, okay, so let's try this question. Here I'm looking at just the magnetic field of a traveling wave. So there is an electric field, but I'm not showing it. And I've just taken a snapshot at the moment, and I'm asking if this is the function of the B field. The B field is a function of space and time. Then what is the direction in which it is moving? And stop. All right, so large result for positive y, and that is correct. So if we look at the function, we see that, oh, okay, ignore the b naught k hat outside. That tells you about the direction that the B field is pointing in, but it doesn't tell you which way the wave is traveling. For that, we look at what lies inside the function. So we have sine of ky minus omega t, and we remember that, oh, if it's y minus vt, then it's moving in the positive y direction, right? As t increases, y has to increase to compensate. So that is the idea going on here. So it's moving in the positive y direction, right? So even if I don't give you the E field, if I just give you the B field as a function of position and time, you can tell which direction the wave is moving in. All right. So now let me ask this. All right, any last votes? Okay, so it's a close split on this one, 41-52. So most of you figured out that the E field has to point somewhere along the X direction, either plus I hat or minus I hat needs to be the direction. And that's correct, because we know that the E field, the B field, and the direction of propagation all need to be perpendicular. And we already have the B field along the Z direction. We know it's moving in the positive Y direction. So that leaves only the X direction for the E field. But now the question is it plus I hat or minus I hat outside? Well, remember that we want to get E cross B should give us the direction of propagation, right? So we need something cross K hat should give us positive Y hat, positive J hat. And so we have basically two options. We have plus I hat or minus I hat. So let's try. So if we do I cross K, that gives us minus J hat. Right. So remember that one way to remember the cross product is you just write ijk, right? And so that tells you I cross j is k, j cross k is I, k cross I is j, right? If I do I cross k, I'm going in the reverse direction, so I get minus j, right? So if I want to get positive j, I'm going to need another minus sign. So B is the right answer there.
How do you know that to get the direction of propagation, you need to go to E cross B?
Say again?
How do you know that you need to do E cross B?
Because that was the pointing vector.
But why does that give you the direction of propagation?
Because remember, the pointing vector shows which direction the energy is flowing. And
that also says something about propagation?
Yes, because the idea is like as the light is propagating, the energy, it's taking the energy and making it move. So those directions will be the same.
I see.
All right. Okay. So we have that, we have that. Let's try one more of those. Okay, again, pretty close, but slight edge for A, 52 to 36. So let's see. So we have an E field. The E field is pointing in the Y direction, but we can see that the wave is moving in which direction?
The negative, the
Yep.
negative.
Exactly, the negative k hat direction. So we want J cross something should give us negative k. And in fact, J cross I will give us negative k. All right. So A is the correct answer there. And, okay, and here, I'll skip over this one, but here, if you're given E naught, you can figure out what V naught is because you know the speed of light in vacuum. And we know that E over B should give us the speed of light. Okay. So we've been talking about the direction of the pointing vector, but what does the magnitude of the pointing vector actually relate to? So it turns out there's an easy interpretation for light. What does the pointing vector represent? It turns out that the intensity of the light is the same as the time average of the pointing vector. And so what exactly is intensity? Intensity is power over area. All right, so let me just write that here as well. So yeah, so intensity is power per unit area. So you can see that the units would be watts per meter squared or joules per meter squared times seconds. And so we can show that the pointing vector, the magnitude of the pointing vector is related to the intensity. And so the time average of the pointing vector will give you the intensity of the light. To get a bit of an idea about intensity, often what we say is that the source of the light is giving out, it's radiating power. And if we imagine a point source, then it's radiating out in all directions. And we can imagine that as the light spreads, so initially it's a small sphere, and then it gets larger and larger, right? And so the same power is being distributed over larger and larger areas. So that's why as you move further away from a light, it gets less intense because it's still giving out the same amount of energy, but that energy is being spread over a larger and larger sphere, right? And the area of the sphere goes as 4 pi r squared. So as you get further and further away from the source, r squared becomes bigger, and so the intensity drops off as 1 over r squared.
Why is it not 2 pi r squared?
Why 2 pi r squared?
Isn't that the area of a...
No, 4 pi r squared is the surface area of a sphere.
Oh, surface area.
Oh, sorry, yes, yeah.
So is it power over surface area or power over area?
Power over, I'd say surface area, basically. Yeah, it depends upon what shape your light is spreading out in. So if it's just spreading out in all directions, it's spreading out in the, as a sphere, basically. If you just imagine a pulse of light, just switch on, switch off, it spreads out in all directions as a sphere.
Oh, I guess surface area would make sense because you're not going into the,
yeah,
inside of the...
Exactly, yeah, you're just standing at one point and this pulse goes just by you. So you have this sphere of light just propagating and it passes by you. All right, clear those drawings. And so we can relate that Poynting vector average to the magnitude of the electric field. So we see that the intensity of light goes as the square of the electric field amplitude. And if you go further into optics and start looking at interference and phenomena like that, that has some interesting consequences there. All right, we're just about out of time. Is there anything else I want to say? All right, well, just a small point. So electromagnetic waves not only carry energy, they actually also carry momentum. And so light particles, so photons, when they hit you, actually transfer momentum to you. But of course, you know, when you go out in the daylight, you're not like hurtled to the ground by like the blast of solar radiation. So you can imagine that each photon of light carries a very small amount of momentum. And in fact, it's the radiation pressure is given by the intensity over the speed of light. And since the speed of light is pretty big, the radiation pressure is usually very small. But it can be detected, and it has effects in space, for example. Over many, like millions of years, the orbits of asteroids, for example, can be affected by the radiation pressure. And you can also, we know from momentum and like collisions and all that we learned in 113 that if you have a inelastic collision, that gives some momentum transfer. But if you have a bouncy elastic collision, that actually gives you more momentum transferred. And so you actually pick up a factor of 2 if you have perfect reflection there. And this is the idea behind solar sails. So you might remember a few years ago that I think it was Yuri Milner and Stephen Hawking said that they were going to set up I forget what they called it, but basically it was an initiative to send a sort of probe to, I think, Alpha Centauri or Proxima Centauri, probably Proxima Centauri. And the idea is that it would be powered by a solar sail, because you don't have enough rocket fuel. It would be too expensive to get rocket fuel to push you all the way. But instead, you just take advantage of the radiation coming off of the sun and just reflect it. And that gives you a little bit of a push. And in space, you know, you don't have to worry so much about drag. If you have a large enough area, you can just accumulate enough momentum from just reflecting all this light, and that will speed you up to a decent speed. All right, we'll be ending there. Harrison, you had a question?
Is a photon the same thing, or is it different from an electromagnetic wave?
So that gets a little complicated. For our purposes, we're going to use them interchangeably, but technically speaking, like you have to go into quantum mechanics to understand exactly what's going on there. But yeah, we'll mostly be talking about electromagnetic waves. I might say photons sort of colloquially, but yeah, we're talking about electromagnetic waves. All right. I know today was a little fast. Had to just kind of bring the pace up a little bit, but feel free to ask me questions. But otherwise, that's it for today. All right. Thank you.
Thank you.
Dr. Black,
Hey.
how can the is there a mass associated with electromagnetic waves? And if not, how can they carry momentum without a mass?
Good point. So no, there is no, well, there's no what we call rest mass for light. The reason why it can still carry momentum. Well, I mean, basically what happens is that we need to generalize our concept of momentum beyond just P equals mv. Yeah, so we can't really assign a mass to light, but we do see that it exerts a push. So you can like measure a force. If you expose a surface to light, you can measure the force of the light on that surface. And so we realized that, yeah, it has to transfer momentum. And also, in fact, what you can show is that if you look at two charged particles approaching each other, and you look at the magnetic force they exert on each other, you will see that if you just look at the magnetic force of one on the other, and vice versa, it appears to violate Newton's third law. Like the directions of the forces are not, the magnitudes are equal, but the directions are not opposite directions. So how do we resolve that? So it turns out what's actually happening is they're not interacting directly with each other. Each charge is interacting with the field, and then the field interacts with the other charge. And so the field is actually carrying momentum. Once you take that into account, so you can define momentum for electromagnetic fields. Once you take that into account, you can rescue momentum conservation.
Okay, thank you so much.
Mm-hmm. Other questions?
Yeah, I had a quick question about just the grading.
Oh, okay.
So would there be like any way, I know a few of my other professors are doing that, where for deciding pass fail, we can give you like a kind of like a cutoff grade or something similar to that?
Oh,
or
so
just a way to like know what our grade, like about what our grades would be before the end of the semester?
Right. So definitely, like once I've finished grading the second midterm, I'll update all the other scores as well, so that you can see like roughly what your projection is. I'll have to consult with Dr. Voth, but I would say something like a C minus is and above is a pass.
Okay. All right, thank you.
Mm-hmm.
Hi, so I wasn't able to go to the lecture live on Monday, but I had one question about what you covered.
Uh-huh.
Maybe if I just share my screen to show, there's just one specific question.
All right, let me just stop my share.
Okay.
All right, go ahead.
Right. Okay, so it was about this one. So I guess I was just confused because like if you're thinking about the pointing vector in this case, you said that the pointing vector is like pointing towards the wire with the current. So I guess in that case, I was like thinking about that in the sense that energy is flowing into the wire. So then I was thinking that that would mean that the current is increasing. So I guess I was just wondering why that like method of thought doesn't work in this case.
Sure. I would say that I guess I'd put it more that the energy is flowing. So the energy was stored in the magnetic field in the middle of the solenoid. And so now it's flowing away from there. And it is, remember that a solenoid is also essentially like an inductor. So it doesn't like the current running through it to change. So the reason why it's trying to supplement the current and help it out is because the current is originally failing.
Oh, I see. Okay. Okay, that makes sense.
All right.